In many physical problems, we need to find the particular solution that satisfies a condition of the form y of t sub 0 equals y sub 0. This is called an initial condition, and the problem of finding a solution of the differential equation that satisfies the initial condition is called an initial value problem. In this example, we first want to show every member of the family of functions given is a solution to the given differential equation. Notice first that y prime is in the differential equation, so we'll start by finding y prime. The first derivative, we'll need to use the quotient rule. We have the denominator times the derivative of the top minus the top times the derivative of the bottom, which is just 1, all divided by the denominator squared. And we can simplify this a little bit. Y prime will be 1 minus natural log of x minus c, all divided by x squared. And now we'll plug this into the differential equation and just confirm that we get a solution. So plugging into this equation, we have x squared times y prime. Y prime is what we just found. 1 minus ln x minus c divided by x squared plus x times y. Y is the initial equation that we were given. Ln x plus c divided by x. And we're trying to prove that this is 1. We want it to be 1 if this is indeed a solution. First, notice the x squared will cancel. 1 minus ln x minus c plus, here the x's go away. That's ln x plus c equals 1. And now we get 1 equals 1. This is a true statement. 1 does equal 1. Since it's true, we can say that y is a solution to the given differential equation. In part B, we'll illustrate this in the graphing calculator. In y equals, we'll type in the functions. There's a fraction, so I like to use alpha y equals and then enter to get that pretty fraction. Then ln x. The c values, let's go from -2 to +2. So we'll start with -2, and then we're dividing by x, and then we'll just repeat that process for other c values. And when we graph it, we can see what's happening with this class of functions. If you want, we can zoom in a little bit. We're going to zoom box. Zoom number 1 to get a better zoom window. So what we have here is several different graphs of the solutions to this differential equation. In part C, we want to find a solution of the differential equation that satisfies the initial conditions. So here we're looking at an initial value problem. We're given some initial information. Recall that y is equal to ln x plus c divided by x. So with this given initial condition, we'll have 2 equals the natural log of 1 plus c divided by 1. Solving for this, we'll get that c is equal to 2. So the solution would then be y equals ln x plus 2 divided by x. That's one of the equations that we graphed earlier. And then in part D, we want to find a solution to the differential equation that satisfies this new initial condition. Y of 2 equals 1. This time 1 equals natural log of 2 plus c divided by 2. If we solve this, cross multiply, we get 2 equals ln 2 plus c, and then c would equal 2 minus the natural log of 2. So y is now the natural log of x. Our c value is 2 minus natural log of 2, and all divided by x. This is the solution to the differential equation with the given initial condition. Now we'll look at a simple application. A population is modeled by the differential equation given. For what values of p is the population increasing? In other words, when is dp dt greater than 0? When is it increasing? We'll assume that p is greater than 0, and if p is greater than 0, 1.2p must also be greater than 0. And if that's the case, 1.2p, if it's positive, we want this piece to be positive as well. So 1 minus p divided by 4200, we want it to be positive, greater than 0. Now we'll solve this inequality. We can add the fraction to both sides. Then multiply by 4200 on both sides. 4200 is greater than p. Or if we reverse that order, p must be less than 4200. And earlier we said that p is positive, so p is between 0 and 4200. When we have this population, the population is increasing. Similarly, we could ask, when is the population decreasing? Using the same logic, 1 minus p divided by 4200 would need to be less than 0. Again, adding to both sides the fraction, and then we get 4200 is less than p. So when the population is over 4200, we have that the population is decreasing. And what are the equilibrium solutions? We want dp dt to be 0. So we'll set that differential equation equal to 0 and solve. We can set each factor equal to 0. On the left equation, we simply get that the population is at 0. And then on the right, again, we add the fraction to both sides, cross multiply, and we get p is 4200. So population of 0 and at 4200, we have equilibrium solutions.